section 9.2, quadratic inequalities in one variable. So solving a quadratic equations by graphing can also be used to solve quadratic inequalities in one variable. Instead of stating the x-intercepts as a solution, the graph is used to identify intervals of x values where y values of the graph are above or below the x-axis. So really what we're trying to do is we're trying to say what values of x make this true. So there's not one or two solutions, there's a bunch of solutions. Okay, so we're looking for regions. The quadratic inequality in one variable can be written in one of four forms. Therefore, there are four possible scenarios. So first of all, if you're looking for the function whenever it's greater than 0, the solution set is wherever the graph is greater than 0. So here the graph's greater than 0, there the graph's greater than 0. So we're talking about this region here and that region there. So we say all x that are less than 1 and all x that are greater than 5. Notice we have these big circles. We say we're not including that. There's no equals to. Okay? When we include that equals to, then we include those points as well. So it says, where is this function greater than or equal to 0? Well, everything here and everything there. Okay? In this graph, it says, where is the function less than 0? Well, you can see the function is less than 0 here. So all the x values in between there would give us values of y that are less than 0. So what we do there is, again, open dots because, and we say everything x is between 1 and 5. Here it's included because we said where it's less than or equal to 0, we include those points, and notice that we have equal signs there. Okay, so how do we go about doing this? What we do is it says solve x squared plus x is greater than 6 graphically. First, I need to put my expression on the left side and 0 on the right side. Okay, now I need to go about graphing this. And this is in standard form. In vertex form, we're used to. This is standard form. So what I'm going to do is the axis of symmetry. And the axis of symmetry is equal to negative b over 2a. We learned this a long time ago. Some of you might remember this. So in this case, negative b would be negative 1, because this is a, b, c. 2a would be 2. So negative 1/2. So at negative 1/2, we have the axis of symmetry. Now, if you remember, the vertex is going to be on that axis of symmetry. So I already know my x value of my vertex, which is negative 1/2. And I just need to sub in this value into my function to get my y. So y equals negative 1/2 squared plus, I'm just subbing it in here, plus negative 1/2 minus 6. So this is equal to positive 1/4 plus negative 1/2, let's change that to 2/4, minus 6 would be 24 quarters. Okay, so I have 26, I have 25, negative 25 quarters. And that would be g just less than negative 6. So there's my vertex. Okay, now I just need to find 5 points. And because of that axis of symmetry, I really only need to find 2 more. So let's see when x equals 1. Well, 1 squared plus 1 is 2, minus 6 is negative 4. Because of the axis of symmetry, this is 1.5 away. I can just go 1.5 away on the other side. Okay? Let's try the point 2. So this gave us negative 4. Well, 2 squared is 4, plus 2 is 6, minus 6 is 0. So we are going to put at 2 at 0. Now this is 1, 2.5 away, half, 1, 2. Symmetry gives me this. And I'm going to draw my parabola. Okay? So good review on drawing parabolas. But what I'm asking is when is y is greater than 0? I'm saying when does this function greater than 0? Well, you can see it's greater than 0 whenever I take an x value here and whenever I take an x value there, because these gives me values greater than 0. So what I need to do now is I need to write that in an elegant way. So first of all, no equals to. Okay, so I actually have open circles there. So I say all x such that x is less than this number, and that number is -3. And, second, I need to look back. How do I write and? I think I just do a comma. Oh, they write or here. Or x is greater than 2. And x is a real number. So that means I could take real numbers, I could take halves, I could take all the little points in between here. Okay, so that is my solution. All x such that x is less than -3 or x is greater than 2 will give me a y value of greater than 0. So let's choose a test point. Let's see if that's true. Okay, so let's choose this point right here. That is x is equal to 1, 2. 1, 2, 3, 4, 5. So if I sub in 5 squared plus 5, I'm saying that that's greater than 6, according to my original equation. And is that true? Is 25 plus 5 greater than 6? Yeah. The other thing I said is that if I choose something not in the solution, if I chose the point 0, it would not be true. 0 squared plus 0 is greater than 6. That's not true. Okay, so quick little checks you can do to make sure you've done this correctly. Let's try another one. Solve 2x squared plus 5x less than or equal to 3 algebraically using roots and test points. Oh, wow, roots and test points. Okay, so what we're going to do here. Okay, first thing we're going to do is we are going to rewrite so we have a 0 on the left side. And we always want to move, we always want the quadratic on the left and the 0 on the right. So 2x squared plus 5x minus 3 is less than or equal to 3. Oh, is less than or equal to 0. I'm going to factor. Okay, so I need two things that are going to multiply to be -6, add to be 5. Well, that looks like 3 and 2. No, that doesn't work. It's going to be 6 and 1. It's going to be 6 minus 1. So I rewrite that middle term. 2x squared plus 6x minus 1x minus 3 is less than or equal to 0. Now I group. In this first one, I can factor out a 2x. I'm left with x plus 3. Here I can factor out a -1, and I get x plus 3. Okay, so I factor out the x plus 3. I'm left with 2x minus 1. Okay. Now I factored and I need to find out the roots. So here we have x equals -3, and here we have x equals 1/2. So I just set each of those to be 0. Now I draw a number line. Okay, so, and I put my roots on it. I have -3 and I have 1/2. So it's just like a number line. I start negative and I go to positive over here. Okay, now for each interval I need to choose a point that falls within the interval, and I have to test in the original inequality to see if it's true or false. So I'll put my test points in 0. I'm going to start here. This is the easiest one. The test point is 0, because that's between -3 and 1/2. So if I do the test point as 0, if I sub it back in here, if I have 2 times 0 squared plus 5 times 0, okay, minus 3. Is minus 3 less than or equal to 0? Yes. So this is one of the solutions in between here. I still have to do a test point on this part, so something bigger than 1/2. Let's try 1, and let's put that in our original equation. 2 times 1 squared, so 2 times 1 plus 5 times 1 minus 3. Is that less than or equal to 0? 2 plus 5 is 7 minus 3. 7 minus 3 is 4. Is 4 less than or equal to 0? No. So we're not talking about this region. I still need to test this one. So I could do -5. I could do -3,456. But I'm going to choose something easy. I'm going to do -4. Okay, that's probably the easiest of those numbers. So it's 2 times negative 4 plus 5 times negative 1 minus negative 4, sorry, minus 3, is that less than or equal to 0? Well, 2 times negative 4 is negative 8, plus 5 times negative 4 plus negative 20 minus 3 less than or equal to 0. Okay, I have negative 8 plus negative 20 minus 3 less than or equal to 0. Oh, I forgot to square this. That's my problem. 2 times negative 4 squared. Negative 4 squared is 16. 2 times 16 is 32. There we go. 32 plus negative 20 would be negative 12, would be positive 12, minus 3 would be 9. And is 9 less than or equal to 0? No. So I'm not talking about this point. So my region that is correct is this region right here. Looking back, do I have equal to? I do have an equal to. So I'm talking about these points as well. So now I just need to describe this region shaded in here. So that would be x is less than 1/2, or equal to, because we had an equal to in the question, but it's greater than or equal to negative 3. So I usually start in the middle and work my way out. The other thing to remember is if you get a case where it's these regions on the outside, that's when you do the or. It's this or this. When you have something snuck in between, that's when you do it like this. So to write it correctly, we would say x such that x, negative 3 is less than or equal to x, which is less than or equal to 1/2, and x is a member of the real numbers. Okay, so we can do another example together. The two methods I showed you there, we can use algebraically using roots and test points, or we could do it graphically. Okay?